Hello and welcome to this video. This is a continuation of my last video on calorimetry questions in the thermochemistry unit for Chemistry 30. In the last video for part 1, the calorimetry questions that we were looking at were calculations where a specific mass of a substance was reacting. In this section, we're going to look at what happens in calorimetry questions when you're given solutions, and solution information given is usually concentration and volumes rather than dealing with the mass of a reacting substance. So it's important to note that a solution is just water with a little bit of a compound dissolved in them. So if I'm giving you the volume of a solution, sometimes students think, for example, if I have HCl. If I have a certain volume of HCl, they think that that volume is only of the HCl. It's like 100% liquid HCl. That's not true, okay? There is a tiny bit of HCl liquid, perhaps, dissolved in a vast majority of water. So when you have a solution, it's important to note that the solution volume is essentially the volume of your water in the calorimeter system. Now, if you're mixing two solutions, then the total volume is going to be the volume of water that makes up your calorimeter and that surrounding environment, and that volume in milliliters equals the mass in grams. Okay, because remember the density of water is 1 gram per milliliter. So if you know that you have added, let's say 100 milliliters of solution A, which is mainly water, 200 milliliters of solution B, which is mainly water, you now have 300 milliliters of mainly water. Okay, so that 300 milliliters would equal 300 grams in our water side of the calculation. Now, the other thing is how we're going to solve for N of the reacting substance on our reaction side, which is NH. The N of the reacting substance, rather than mass over molar mass, is going to be found with C times V. Now, because of our unit analysis, remember again, concentration is given in moles per liter. So that means if I'm multiplying by a volume of my reacting substance, I need to know the volume in liters. So the liters can cancel and leave me with the units in moles. We'll look at a couple of examples and see how you deal with, I call this solution calorimetry. So a student is mixing 100 mils of 0.5 mole per liter hydrobromic acid with 100 mils of 0.5 mole per liter potassium hydroxide. The initial temperature of the solutions are 21, and the highest temperature reached after mixing is 24.4. Calculate the molar enthalpy of neutralization in kilojoules per mole for the HBr. That's important. We have two reacting substances. Whenever you're looking for molar enthalpy, it can be for either substance. So you have to read the question very carefully to see which substance it wants you to find the molar enthalpy of. Okay, it does put a note here that assuming the solutions have the same density and specific heat capacity of pure water, even though again, remember the solutions have some of those compounds dissolved in them, we're going to assume they're just water, right, for our calorimetry calculation. So like before, we start by looking at what's happening to the water, the solutions being the water, okay? Maybe make a note for yourself there that the solutions are your water. That's what a solution is. Okay, and the temperature of the solutions or the temperature of the water is increasing, so that means our reaction is exothermic, meaning again we're going to need to put a negative value in front of our answer. And when we set up our equation, the heat is being lost by the reaction. And again, specifically HBr is what I'm focusing on, the molar enthalpy of, so I'm going to say the reaction of HBr, okay? And the heat is being gained by my water or your solutions. You can put solutions there too if it makes it easier, but I like to put water because that again is what we're using the specific heat capacity and density of. So like before, Our reaction side always starts with delta H. Anytime you have a reaction, you're measuring delta H. And anytime you have water, because it's going through a temperature change in calorimetry, you're going to have Q. So my delta H of the reaction equals the Q of the water. Now, if I replace those with their formulas, delta H equals NH, and Q equals MC delta T. So a lot of times students will start at this line, where NH equals MC delta T, and that's totally fine, okay? Now the question is, I'm dealing with, again, my moles of the HBr. So how we're going to find the moles of HBr specifically is going to be because I have a concentration and a volume given, not a mass. So it's not going to be molar mass, mass over molar mass. I'm going to replace the N with C times V. That's how I'm going to find my volume, my moles of HBr, C times V. Okay, so now if I do that calculation, my concentration, again, this is of HBr that we're focusing on, the C and V for. So the concentration of HBr was 0.500 moles per liter. That's coming up again from right up here. And my volume has to be in liters to get liters to cancel. So if you have a milliliter and you're wanting to convert it into liters, there's a couple of ways you can do it. If you look at 100 milliliters, a milli on your data booklet on page 3 is 10 to the power of -3. So you multiply by 10 to the power of -3. Now that's the same as saying you're dividing by 1,000. Okay, so however you want to remember it, you're essentially dividing by 1,000. So that means this wasn't very neat here. That means my volume is 0.1. Technically, it has the same sig digs. Do you have to write all those zeros? No. But this is technically, when you convert something, you keep the same number of sig digs in it. Okay, so my liters cancel, and I am left with moles of HBr on the left-hand side. On the right-hand side, we're going to do our MC delta T calculation of the solutions, which are the water. The solutions are the water. I'm taking 100 milliliters of HBr and 100 milliliters of KOH, and I'm mixing them together to get a total volume of 200 milliliters, which is equivalent to 200 grams, 200.0 to be accurate. 100.0 plus 100.0 is 200.0. So to get the amount of water you have, you add the volume of the solutions that you're mixing when you're mixing two solutions. Okay? This is why, like I said, I put water information here instead of saying solutions, because I know what am I using the specific heat capacity of. I'm using the specific heat capacity of water. Water is 4.19. And now my temperature change. My temperature change, I'm actually just going to put the calculation in here. 24.40 minus 21.00 degrees Celsius. Okay? And that will be my calculation on my water side. My grams will cancel, my degrees Celsius will cancel, and we will be left with an answer in joules. And since we're solving for H, I need to divide both sides. If I just ignore these units for a minute because they canceled, I'll be dividing both sides by 0.500 moles is the units I'm left with there, times 0.100. So that cancels there and becomes divided over here, 0.500 moles times, I'm running out of space. I'm going to erase these units now because they all canceled. You don't have to erase units, but I'm just doing that to make some space. 0.100 liters was what that other number was, but those liters canceled. So I'm now left with joules per mole after I complete my calculation solving for H. Okay, so it would be 200 times 4.19 times, in brackets, 24.4 minus 21. Then you divide by 0.5 in brackets times 0.1. And we get an answer of 0.56984 joules per mole. Remember, this is not our final answer. There's a couple of things we have to do. It's asking again for kilojoules per mole, so I'm going to divide by 10 to the power of 3, or 1,000. And then, remember, if I go back up, I have lots of circles and lines here, but if I go back up to the very top, this reaction was exothermic, so I need a negative in front of my answer. Okay, so when I divide that by 1,000 and put the negative, and how many sig digs can we have? Looking back up at the question, my volumes have 4, but look at the concentrations. Leading zeros don't count. So there's only 3 sig digs in the concentrations. The temperatures also have 4. So out of everything, the lowest is 3. So if I round this answer after I divide by 1,000, we get negative 57.0 kilojoules per mole for our final answer. Okay, that is the molar enthalpy of this neutralization reaction for the HBr, because we use the moles of the HBr. Okay, so negative 57.0. If you are unsure how I got that, when I divided this by 1,000, I got negative 56.984. If I'm rounding it here, the 9 rounds the 6 up. That's why it becomes negative 57.0. Whenever you're cutting off a 5 or more, it rounds the last digit that you're keeping up by 1. Okay? Let's look at a sample diploma question. This is a numerical response question. So we are told we have a calorimetry experiment. That's always nice to know for our setup, that it's calorimetry. But again, you know it's calorimetry if you have reacting substances, solutions specifically, which can act as water. So you have reacting substances and water, essentially. Okay? This is a solution calorimetry question. You have solutions being mixed, initial and final temperatures. Okay? Now, let's look at what's happening to the water. The water's temperature is going up. So again, if the water temperature, again, the solutions being water, aqueous means water, if the temperature of the water goes up, that means that my reaction is exothermic. And so again, it needs a negative symbol in front of it. Now, how do you put a negative in numerical response? There's never a negative or positive symbol that you can put in numerical response. But notice how this question, for your numerical response answer in the first column, it says if it's positive, record a 1, and if it's negative, record a 2. So we're going to be recording a 2 in front of our answer because this is an exothermic reaction. Not all numerical response questions ask you to do this. Most of the time, it'll say positive/negative, what is the value in kilojoules per mole, for example. And then you're just putting the value. You're not circling positive or negative, you're just putting the value, whatever the value is, whether it was positive or negative. Okay, that's how a lot of numerical response questions work. But this one is actually asking you to put a numerical value, whether it's positive or negative. Okay, so since this reaction is exothermic, I'm going to set it up as heat being lost by my reaction again, because it's exothermic. Now, what are we looking for? We are looking for the molar enthalpy of hydrochloric acid. Hydrochloric acid is HCl. So I'm going to set this up as my heat is being lost by the reaction of HCl, and it is being gained by the solutions, which are the water. Okay, solutions are the water. So I'm going to go straight to concentration times volume times H. So that's, remember, my formula for delta H, NH, and N coming from C times V. And my water is going to be Q. To solve for Q, we use MC delta T. Okay, so I'm just going straight there because we don't have a lot of room on this slide. So I'm using the concentration and volume in liters of my HCl on the left-hand side. So my concentration of HCl is 0.250, and the units again are moles per liter. and I'm multiplying that by my volume in liters of HCl. So I have to divide that by 1,000. It's 0.1000 liters. Okay, and that gets multiplied by H, which is what I'm solving for. My liters cancel, so we're left with moles again. Now on the right hand side, I'm again doing everything about the water. The water again being the solutions. That's what the solutions are. Okay? So my total amount of solution is my total amount of water. I had, if I erase all my writing here, 100 milliliters of HCl mixing with 100 milliliters of sodium hydroxide. So in total, I have 200.0 milliliters of my solutions, which is my water. So that is equivalent to 200.0 grams of water. The volume in milliliters equals the mass in grams. Water specific heat capacity is 4.19 joules per gram degree Celsius, and my temperature change is 40.5 minus 25.5. I always take the bigger number and subtract the smaller number. Okay? Now, again, to solve, I'm going to need to divide both sides by my n, which was 0.250 times 0.1. I'm just going to write 0.1 because I'm running out of space here. Okay? So my grams cancel, my degrees Celsius cancel. We're left with joules per mole after I do my calculation. Okay, and notice again, look at what units it wants your answer in. For the SIG-DIG question, it wants kilojoules per mole. So when I do this calculation, I'll have 200 times 4.19 times brackets 40.5 minus 25.5. Then I divide that answer in brackets by 0.25 times 0.1. We get an answer of 502,800 joules per mole. I need to put a negative in front of it because, again, my reaction was exothermic. And I need to divide it by 1,000 to put it into kilojoules per mole. So when I divide by 1,000, that gives me negative 502.8 kilojoules per mole. And it looks like we can have only 3 significant digits. So if I round that off, I'm not cutting off the decimal, so I don't need to put it into scientific notation, but I'm cutting off an 8. So that's going to leave my answer. My H is going to be negative 503 kilojoules per mole. Okay? So the first column is going to be a 2 because it was negative. And then the second, third, and fourth column is my numerical answer, which was 503. So if this is a numerical response question and you're putting it into those 4 boxes, you would put 2503 for your answer. Okay? So there's a couple examples of solution calorimetry questions. Let's look at another part of calorimetry where you might be asked to find your answer instead of kilojoules per mole, kilojoules per gram. Okay? There's a couple of ways we can do this. If we have an answer already in kilojoules per mole, kilojoules per mole, I can divide it by my molar mass. Divide by the molar mass of the substance. Okay? If I divide by the molar mass, I'm going to have grams per mole at the bottom. This will end up moving up here. Okay? So what's going to happen is our moles cancel and we're left with kilojoules per gram. Okay, so if you have kilojoules per mole, you can divide by the molar mass to get kilojoules per gram. That's one way of converting an answer in kilojoules per mole to kilojoules per gram. But there's a second way that we're going to look at, okay? And that's where you set up your equation for your reaction side. Instead of writing NH, we're going to put MH, okay? That's what our second example is going to look at. Our first example is going to look at converting a kilojoule per mole answer, and then the second example will look at using that formula instead, okay? So let's do some examples. I have a 1.50 gram sample of methane completely burning in a calorimeter containing 2.50 kilograms of water. The temperature has increased from 20.15 to 27.45 degrees Celsius. Calculate the molar enthalpy of combustion for methane in kilojoules per mole, and then convert your answer to kilojoules per gram. So this is a normal sort of calorimetry question. This is a good spot where you could practice making sure you know how to start this question. Doing the kilojoules per mole. This is a mass type of kilojoules per mole question because we have the mass of our methane burning and we're looking for the molar enthalpy of the methane. So the methane is what we're focusing on, which is CH4. The water in the calorimeter, temperature is increasing. So because the temperature is increasing, this is an exothermic reaction, which means we're going to need to put a negative in front of our answer. So I also set it up. The heat is being lost by the reaction because the reaction is exothermic. And I'm focusing on methane on my reaction side. And the water is gaining that energy as its temperature is increasing. Okay? So I'm going to have NH for my reaction side equals MC delta T for my water side. Okay? My N I'm going to find with mass over molar mass because I have a mass this time, not a concentration and a volume. So the mass of the methane is given in the question. It is 1.50 grams, and I need to divide by the molar mass of methane. Methane is 1 carbon, carbon is 12.01, and 4 hydrogens, which are 1.01. So I get a molar mass of 16.05 grams per mole, and I'm multiplying that by my molar enthalpy, which is what I'm going to be solving for. So I'm just going to leave it as H. The mass of my water is given in kilograms up here. So remember, we have to convert that into grams. So multiply by 10 to the power of 3. I'm going to multiply that by my specific heat capacity of water, which is 4.19 joules per gram degree Celsius, and I'm going to multiply that by my temperature change of 27.45 minus 20.15 degrees Celsius. Okay, remember there's no numbers on the bottom of the division right now. I'm just doing that to show unit analysis and how grams and degrees Celsius cancel, so we're left with joules on the top. Now I am going to need to divide both sides by my mass over molar mass, so that moves it down here, 1.50 grams. Actually, the grams, I could write the grams again, but they're canceling, and we're left with moles. Okay, so I'm just going to leave this as moles divided by 16.05. Okay, so I'm left with an answer in joules per mole, and again it's asking for kilojoules per mole. So if I do this calculation, 2.5 times 10 to the power of 3 times 4.19 times, in brackets, 27.45 minus 20.15. We then hit divide by 1.5 divided by 16.05 in brackets. We get an answer for our H of 818,202.25 joules per mole. Now, I'm going to put a negative in front of that answer because, as we established at the beginning, this is an exothermic reaction. So I need a negative, And again, most commonly, it's going to ask you to put it into kilojoules per mole. So we divide by 1,000. So we're left with an answer of negative 818. There's a 0.2 after it. We can leave it to 3 sig digs. So it'll be negative 818 kilojoules per mole. For our first answer, it then is asking us to convert it to kilojoules per gram. Okay, so all we need to do is take our answer. Our H was negative 818 kilojoules per mole, and I need to divide by the molar mass. So on the bottom here, I'll have 16.05 grams per mole on the top. So my moles cancel, and we're left with kilojoules per gram. So what I do is I take my negative 818 and divide by 16.05, and we get an answer of negative 50.9 so on. Or sorry, I should put what that is. 50.96 so on kilojoules per gram. And again, we realized we could only have 3 sig digs, so I'm going to cut it off here. This 6 is going to bump the 9 up. And since the 9 is bumping up, it bumps the 0 up. So this is going to round to negative 51.0 kilojoules per gram. That is our second converted answer from kilojoules per mole to kilojoules per gram. I divided by the molar mass of my methane. Okay, that's the first way of solving for kilojoules per gram. If you have an answer in kilojoules per mole, you can convert it. But the second way, which is more common to what you're going to see, is you're going to have questions where you have a compound or a mixture, I guess, a substance. How do I find the molar mass? What is butter? What is the formula of butter? Butter's a big mixture of things. So how do I find the molar mass of it? We are not going to find the molar mass of it because we are not going to find the moles of it. We are not going to find kilojoules per mole. We are going to find kilojoules per gram. Okay? So we're setting this up a tiny bit differently. Now I'm still focusing on water. Water's temperature is increasing. So this means if the temperature of water is increasing, I again have an exothermic reaction. This is a negative reaction. Okay? The heat is being lost by my reaction of butter. Okay, I don't have a formula for that. I'm just going to write butter. It's an exothermic reaction. It is being gained by the surrounding water. Now, rather than writing NH on my reaction side, I'm going to put MH. Okay, that's the difference. It's not NH, it's MH. The water is still MC delta T. So when I solve for H, I'm going to be dividing by the mass of butter on both sides. That's why it's not going to give me an answer in kilojoules per mole. It's going to give me an answer in kilojoules per gram, which is the only thing I can do when I'm dealing with a substance like butter or peanut butter or olive oil or bubble gum, whatever the case is. It's some weird mixture substance that we can't find the formula or molar mass of. You're usually asked to find it in kilojoules per gram. So my mass of butter is 3.00 grams. I'm going to multiply that by H, which I'm solving for. And my water is 2200 grams, 2200 grams. My specific heat capacity, by now you should definitely have that memorized for water, 4.19 joules per gram degree Celsius. And my temperature change is 31.89 minus 19.62. Okay? Close that other bracket. So our grams cancel, our degrees Celsius cancel. I'm left with joules on top. And then again, to solve for H, I need to divide both sides by what H is multiplied by, which is 3.00 grams. Okay, so it cancels over here. And we're left with H equals, in my calculator, I'll be doing 2200 times 4.19 times, in brackets, 31.89 minus 19.62. Then I hit divide and I put 3.00. And we get an answer of 37701.62, and our units are joules per gram at this point. It is asking for kilojoules per gram, so I'm going to divide it by 1,000, and because it's exothermic, put a negative. You'll see that most reactions are exothermic, especially if they're combustion reactions. This is another, not a hydrocarbon combustion, but it's a burning substance. So usually when you burn something, when you neutralize acids and bases, they're exothermic, they're releasing energy. So if I divide that by 1,000 and put the negative in front of it, my answer for H, which again is in kilojoules per gram, is negative 37.7 kilojoules per gram, not per mole. Okay? This is how we solve a question, like I said, of an unknown substance, like butter. We don't know what its mass, we don't know what its molar mass, what its chemical formula is. So it's kilojoules per gram. I believe we have another sample diploma question, and then that is it. So here's another question where it says you have canola oil. What is canola oil, right? Look at the units for your answer. It's saying kilojoules per gram. Okay, so I'm going to be setting it up like we did in the last example. Water's temperature is again increasing, so if the temperature of water goes up, this reaction is exo. Hopefully you guys have done this enough times now. You have that definitely memorized. Exothermic reactions, they lose heat. So my heat is being lost by my reaction of the canola oil. I'm just going to put oil for short. And it is being gained by the surrounding environment, my calorimeter, which contains water. So again, I'm setting it up as MH instead of NH equals MC delta T. Okay, this is the mass and everything to do with my oil. This is my MC delta T of water. So the mass of the oil was 0.150 grams, written up here. That's going to be multiplied by H, which I'll later be solving for. The mass of water, remember the volume in milliliters equals the mass in grams times 4.19 joules per gram degree Celsius, and we are nicely given the temperature change here. We don't have to solve for it. So my grams cancel, my degrees Celsius cancel, we're left with joules, and then I'm going to divide again both sides by 0.150 grams. So I'm going to get left with joules per gram to start. So 450 times 4.19 times 55 divided by 0.150 grams. I get an answer of 691,350 joules per gram. I need a negative because this reaction was exothermic. I divide by 1,000 to convert it into kilojoules. We get an answer of negative 691 to 3 sig digs kilojoules per gram. Okay, this is another question where it's asking you to put a 1 or a 2 if it's positive or negative. It was negative, so we put a 2 and then a 6, 9, 1. So again, on a numerical response answer sheet, your 4 boxes would be 2, 6, 9, 1. Okay, make sure that answer is correct. 2, 6, 9, 1 is the answer. Okay, so that is it for calorimetry and the different styles of calorimetry questions that you could be given. Thank you for watching this video.